Hey everybody, we're live and in stereo. So today we'll be covering the last aspect of acid-base equilibria, which is titration curves. And I've given you guys so many prerequisite classes that now hopefully titration curves and understanding titration curves is going to be a piece of cake. Although in your course, titration curves in its utmost in its utmost reality is never really tested because such calculations are not required as part of your course. But I would love to do one or two calculations with you guys just to give you guys an idea of how these titration curves are actually, how this idea of titration curves was actually developed, right? And how you could calculate stuff throughout this particular experiment, right? Now, what exactly is a titration curve? Basically, what a titration curve does is it shows you how the pH of a solution changes. That's what it does. It shows you how the pH of the solution changes as the reagent in the burette is added to the conical flask. So normally in our course we have acid alkali titrations, acid base titration. So basically what's going to happen is either the acid is going to drip from the burette or the alkali is going to drip from the burette, and in the conical flask you're either going to have the alkali or you're going to have the acid, right? If the burette contains the acid, then the conical flask will have the alkali. If the burette has the alkali, the conical flask will have the acid, right? And so what a titration curve will actually do is it'll tell you how the pH is varying, how the pH varies, or how the pH of this particular solution in the conical flask varies, changes as the reagent from the burette is added to it, right? And understand that the shape of a titration curve actually depends on the strength and weakness, the strength or weakness of acid and base, right? So understand that titration curves largely depends on one thing. It largely depends on the strength, or you could even say the weakness of acids and acids and alkalis. That's what it depends on, right? Now, the first particular titration curve that is a part of our course is when a strong acid is reacted with a strong base. So strong acid reacted with a strong base. How would this curve look like? And in your course, you don't need to know all the calculations. You just need to know how to sketch the titration curve, right? That's it. Now, I want you guys to just follow the first particular experiment through proper calculations with me. Although these calculations will not be tested, they are not part of your course, will never ever be tested. You are just required to sketch it. But before me just making you guys rote learn those sketches, I want you guys to properly understand the gist of it, right? So let's start off with a strong acid and a strong base titration. For example, we'll take HCl and we're going to take NaOH, right? HCl is a strong acid, NaOH is a strong base, NaCl forms. Obviously, NaCl has a pH of 7, we know that, right? And H2O forms. We know acid-alkali reaction, acid-base reaction. It's a strong acid and a strong base. Now, if I were to tell you that, hey, I'm taking 20 cm cube of acid, which is HCl, and it has a concentration of, let's suppose, 0.1 molar, and NaOH that I have, it has a concentration of 0.1 molar. Can you guys tell me what would be the volume of equivalence point? What would be the volume of NaOH that would be added to react with all of the acid? Come on, now we've taken yesterday's class. If you haven't taken yesterday's class, you might not be able to answer it quickly. But if you have taken yesterday's class, you will be able to answer it very, very easily, which is that you would have 20 cm cube of NaOH that is going to be added from the burette into the conical flask, right? Now, that's the idea. So we're starting off with acid in the conical flask. In this particular case, I'm assuming that I'm starting off with the acid in the conical flask, and I'm going to add the alkali, which is NaOH, from the burette, right? So I'm going to start off with the acid and I'm going to add the alkali. And what would be the volume of the alkali that you must add in order for it to react with all of the acid? That's 20 cm cube. We calculated it directly. I've given you guys yesterday's class. You can, if you don't know how this 20 centimeter cube came into being, re-watch yesterday's recording, right? Now, that's good stuff. My question to you guys is, what's the concentration of the acid that I have? It's 0.1 molar. I just said it's 0.1 molar. And what's the volume of the acid that I have? What's the volume of the acid that I have? It's 20 cm cube, right? I want you guys to do a couple of calculations with me. Although again, I repeat, these calculations are not part of your course, but I want to do it just to give you an idea of how you can actually, how this idea of titration curve is actually developed. Okay, tell me something. If you have a concentration of 0.1 molar and you have 20 cm cube of acid, can you guys tell me the moles of acid? Can you guys tell me the moles of acid? N equals CV. How many moles of acid are there initially in the conical flask? Initial moles of acid. Hanji, how many moles of acid do you have? Concentration is 0.1 molar. Volume is 20 cm cube converted into dm cube into 10 raised to the power minus 3. How many moles of acid do I have? Can somebody help me out? It's 0.002 moles of acid. Right? And effectively, you know that whenever an acid-alkali reaction takes place, whenever this neutralization reaction is taking place, it's basically the hydrogen ions in the acid that are reacting with the OH ions in the alkali. Isn't that true? The hydrogen ions in the acid reacts with the OH ions in the alkali. Good stuff. Now, if you have, the acid has, 0.002 moles initially, can you guys tell me the moles of hydrogen ions? Again, it's the same, 0.002 moles, because HCl dissociates completely. All of the concepts that I've given you in the prior classes will now all come into play. We know that HCl dissociates completely. So if you have 0.002 moles of HCl, how many moles of hydrogen ions would you have? 0.002 moles of hydrogen ions, wouldn't you? Initially, you would have these many moles of hydrogen ions. And if initially the concentration of the acid is 0.1 molar, the concentration of hydrogen ions is again 0.1 molar. True. Again, true. We all believe that. Now, if I were to say, hey, this is the conical flask right here, and it has the acid, right? What would be the pH initially? What would be the pH initially of this solution which is present inside the conical flask? If you have 0.1 molar as the concentration, you can write this as 1 into 10 raised to the power minus 1. And so what's the pH for it? The initial pH of this solution is 1. Or you could have used the formula negative log of hydrogen ions, and hydrogen ions are 0.1 molar. So negative log of 0.1 gives me what? 1 pH. A pH of 1, right? Again, these calculations are only taught by me because I want to strengthen your curves concepts. Okay? So although these direct calculations aren't part of your course, pH, how pH is calculated, not part of your course, understand that. Okay? And I've given you guys prerequisite classes of all of this good stuff. So it's good, it'll help you guys now understand titration curves. Done. Now, initially the pH was 1. Now, let's suppose initial pH is 1. I agree. Everybody agrees with me. Good stuff. That's the first starting point. Now what I'm going to do is I'm going to add sodium hydroxide, right? And I'm going to add about 10 cm cube of NaOH. Good stuff. I'm going to add about 10 cm cube of sodium hydroxide from the burette inside the conical flask. Now you all know what's going to happen. The acid had a pH of 1, and the moment you started to add alkali, what should happen to the pH? Should the pH increase or decrease? What should happen to the pH? pH would start to move towards the alkaline end, right? So it would start to increase. True, it would start to increase. Everybody's correct. It would start to increase. Now the question is, how much? What would be the pH actually if 10 cm cube of NaOH is added? Right? We all know that it would increase, but what would be the exact pH of the solution if 10 centimeter cube of NaOH is added? It's pretty simple, and I'll teach you how to calculate it. Again, the calculation is not a part of your course. Please don't be O-level kids asking me over and over again, is this part of your course? It's not. But I want to do this calculation because I've taught it to you guys. Now, 10 cm cube of NaOH is added. Now we know that if 10 centimeter cube of NaOH is added, it would react with 10 cm cube of HCl. Right? It's 1:1. So 20 cm cube of HCl would completely be neutralized by 20 cm cube of NaOH. So if 10 cm cube of NaOH is added, it would have reacted with 10 cm cube of HCl. My question to you guys is, how much volume of HCl would be left? How much volume of HCl would be left? How much volume of HCl would be left after you add 10 cm cube of sodium hydroxide? We all know 10 cm cube of HCl would be left, because 10 of NaOH would react with 10 of HCl, and 10 would still be left because you had 20 cm cube of HCl in the conical flask. So 10 cm cube of HCl would be left. We all agree. Done. Now, What were the initial moles of HCl? Initially, when we calculated the moles of HCl, they were 0.002 moles, right? Right here. Initially, the moles of HCl were 0.002 moles, right here. The moles of HCl or the moles of hydrogen ions were 0.002 moles. Now, my question to you guys is, what would be the moles of HCl after you add 10 cm cube of NaOH? It's pretty simple. It's basically ratio. You realize that 10 cm cube of NaOH reacted with 10 centimeter cube of HCl. So how much HCl is left? Only 10 cm cube of HCl is left. 20 minus 10, 10 is left, right? So if 10 cm cube of HCl is left out of 20, how many moles would that represent multiplied with these initial moles? And if you are weak in math, you could say, hey, for 20 cm cube, the moles that you had were 0.002 mole. So for 10 cm cube of acid left, how many moles of acid would be left? X equals 0.002 times by 10 divided by 20. If your math is weak, you could still stick with cross multiplication, or you could say, hey, 10 over 20, that's 20 were the total. 10 is amount left. So 10 over 20 into the initial moles. These would be the moles of HCl left. How many moles of HCl are left? Everybody, help me out. So I first figured out the volume of HCl left. Now I want to figure out how many moles of HCl would be left. We know it's 0.001 moles. These are the moles of HCl left after you added 10 centimeter cube of NaOH. Everybody agrees with this basic math, nothing else, basic math. Now if you have the moles of HCl, it's effectively also the moles of hydrogen ions, right? It's the moles of HCl are effectively the moles of hydrogen ions as well, because HCl goes into complete ionization. It completely ionizes in an aqueous solution. Now, if I have the moles of HCl, good stuff, or the moles of hydrogen ions effectively, I also have something else. I also have the volume of solution now. What would be the volume of the solution? Please understand that initially you had 20 cm cube of acid, but you added 10 more cm cube of NaOH. So what would be the volume of the solution? The volume of the solution would now increase by 10. It would now not be 20 cm cube, it would be 30 cm cube, right? 20 plus 10. 20 was the initial, 10 was more NaOH that you guys added. So the volume of the solution now is 30 cm cube. And voila, we can find something from this. You had 0.001 moles of acid and you had 30 centimeter cube of solution now. So can you guys calculate the concentration? N equals CV. Can you guys calculate the concentration of acid after you add 10 cm cube of NaOH? Can you guys calculate the concentration? Yes. You have 0.001 moles of HCl. What's the concentration? I don't know. What's the volume? 30 into 10 is power minus 3. Can you guys calculate concentration? 0.001 divided by 30 into 10 is power minus 3. What's the concentration of hydrogen ions, or effectively acid or hydrogen ions? Same thing, potato. What do you get from this? So we get 0.0333 molar. Good. So now that you have the concentration of hydrogen ions, I want you guys to do something else now. You have the concentration of hydrogen ions. Can you guys calculate the pH right now? The pH is what? Negative log of hydrogen ions, right? And so you guys can absolutely calculate it. Negative log of hydrogen ions, which is of concentration of hydrogen ions, which is 0.003. What do you get? It's 1.48. So understand that the moment I added 10 centimeter cube of NaOH, the pH actually increased, and this is the mathematical proof for it. That's the mathematical proof. You went from pH 1 to pH 1.48. You can actually figure out the pH at every single point in time for the solution. And I bet you didn't know that before, right? And again, this calculation is not part of your course, but because I've already taught prerequisites, I've taught you what pH is, how it's calculated, all of that was extra stuff just for this particular day, right? So you can actually figure out the pH now. So after 10 cm cube of NaOH is added, the pH of the solution would now be 1.48. And we all already knew that it's going to increase because you're adding an alkali. So it's going to start to neutralize the acid. It's going to increase. And now we know the exact pH as well, which is 1.48. And I calculated it in a very simple manner. I just said, hey, what would be the moles of acid left? The moles of acid left would now be 0.01 because 20 represented 0.002, 10 would represent 0.001. And so if these are the moles of acid left, these are effectively the moles of hydrogen ions. You have the volume of the solution, N equals CV, found out the concentration of the hydrogen ions. And then I just plugged it in the formula for calculating the pH, which is negative log of concentration of hydrogen ions. And I figured out the pH right here. Now, what if I add 20 cm cube of NaOH? Like I add 10 more cm cube, right? Now I've added a total of 20 cm cube of NaOH. Do you know what the pH is going to be? Because 20 cm cube of NaOH would exactly react with 20 Cl of HCl, and it would neutralize it. You would get a salt, NaCl, and we know the pH for this fella. It's pH 7 right here. So what would happen is, effectively, you are going to go from pH 1 to 1.48, and then the pH would increase up until which point? Up until all the acid and all the alkali have reacted with each other. Effectively, if it's in 1:1, 20 cm cube of acid has reacted with 20 cm cube of alkali. Because at that particular time, there will be no alkali, no acid, you would just have a salt, and in this particular case, the salt will have a pH of 7. And normally strong acids and strong bases, they usually give you a pH 7 salt, right? And this is the NaCl we've already studied in period 3, and we've studied in a lot of places that this would be the pH of the salt, right? Now, part 4, what if I add now 30 centimeter cube of NaOH? Effectively, a total of 30 cm cube of NaOH. So what would actually happen is, if I add 30 cm cube of NaOH in totality, 10 cm cube of NaOH is in excess. Agreed? 10 cm cube of NaOH is in excess. Now my question to you guys is, if 10 centimeter cube of NaOH is in excess, how many moles is that representing? How many moles is that representing? Again, it's the same idea that we used right here. Initially, how many moles of alkali did you guys have? 0.1 was the concentration of the alkali right here. 0.1 was the concentration of the alkali right here, right? And the volume for the equivalence point volume was 20 cm cube. So now if you've added 10 more cm cube, what would be the moles? Initially, can you guys tell me the moles right here at 20 cm cube? Can you guys tell me the moles? You guys can calculate the moles. Or you could even do it directly. You could even say, hey, initially I don't want to do ratio. You could directly do it. You could say, hey, N equals CV. The concentration is 0.1. The volume now, the excess volume is 10 centimeter cube. So 10 into 10 is power minus 3. What do you get? Moles of NaOH in excess. The moles that are left in excess. What's that? 0.001 moles. These are now the excess moles of NaOH that you guys actually have. 0.001 moles, they are in excess. And I can even find the pH for this. Negative log of hydrogen ions, right? And so what you'll realize is that if I were to find out the pH of negative log of hydrogen ions, I don't have hydrogen ions. I have the OH minus ions, right? And we basically find the POH for it. I gave you guys a little idea of what POH is. For basic solutions, you actually end up finding POH, and POH plus pH gives you 14, right? If you take pH and add it to POH, it is equal to 14. I remember in the last couple of classes, I literally talked about this. So POH is the negative log of OH minus ions, right? And so how many OH minus ions do you guys have? 0.001. And what do you get? Again, all of this calculation not a part of your course. I'm just doing it to derive something. This is 1.70, right? So what would be the pH? I know pH plus POH gives you 14, right? So pH would be equal to 14 minus 1.70, and that is equal to 12.30. And this is how you can figure out the pHs at any point in time. So initially you had a pH of 1, and then later on you did your calculations, you ended up with a pH of 1.48. Then at equivalence point you had a pH of 7 because it's a strong acid and strong alkali. And then if alkali is in excess, you ended up with a pH of about 12.30, right? And if I were to show you the table for it, this is how it would actually look. Just give me a moment, hold your horses. Let me show you a beautiful table right now, right here. The moment, peep peeps, just a moment, peep 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 peep, गाड़ी चल रही है, चलते जाओ किधर जावे उधर आवे हम ना नटखट है ना दुल्हा. See, how the pH is changing? Now he, the examiner, or the one who wrote this book, see how he's writing the pH for you? Now the book, all your books will not state how he's calculated the pH right here, but you guys can see it. See, it's at 0, pH was 1 in the conical flask, right? Because that was an acid was present inside the conical flask. When you added 10 cm cube of NaOH, what was the pH? Now the pH was what? The pH now is 1.48, right? And at 15 cm cube, what's the pH? And we actually calculated this 1.48. I actually literally showed you how to calculate 1.48 right here. And this is how the examiner must have, or the author of the books must have calculated it. This is how he does it. At every single point in time, you can calculate the pH. That's how beautiful it is. Right? So he calculated 1.48, then at 15 he calculated 1.85, at 19 he calculated 2.59, at 19.9 he calculated it was 3.60. But at 20, what would be the pH? What would be the pH at 20 cm cube? My question to you guys is, what would be the pH at exactly 20 cm cube? What would happen? It would be, sir, please scroll up. It would be pH 7, right? Here you go, Naima, where do you want me to scroll up? Come on, be quick. Up or upar jaun. Where do you want me to go? So as I was saying that although these calculations aren't a part of your course, now you know how to calculate them. Right? 1, you could practically prove it for yourself. 1.48. See, after 10 was added, you then figured out, okay, how many hydrogen ions are left in the solution, and you figured out the moles of hydrogen ions left, the volume of the solution that was there, and you actually figured out the pH. And at this, it's 1.85. Then it's, and you will see. So as we were saying that you guys can calculate the pH at every single point in time. Right here, pH, 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 pH. Done. Now, what you need to understand is that, hey, at 19.9 of NaOH that you guys added, I'll tell you something. Here, what I meant to say was that you can calculate the pH at any point in time. We calculated 1.48, and similarly all these other pHs are calculated, right? And there are other ways to calculate the pH by using pH plus pOH equals 14, which we use from time to time. At this particular point in time, we'll not make use of it because we are getting some errors in our calculations, so we couldn't care less, you know. But you guys can calculate this stuff later on, and I'll also teach it to you later on. But for now, 1.48 was calculated by us, and then 1.85, 2.59, 3.60, all of these pHs can be calculated. And you know, at 20 cm cube, the pH is going to be 7. Absolutely, it's going to be 7. And we know at 30 cm cube of NaOH that you guys added, the pH is about what? 12.3ish. 12.3ish or 12 point, yeah, right here. It's at 20, it's 7. He's given 20.1 is 40, 10.40, 21 is this, 30 is this. At 40, it's 12.50. When we calculated for 30, what was our pH? What did we get for 30? We got 12.30, exactly the way he got, right? He got 12.30. We also got 12.30 for 30 cm cube. So these are the values of pHs that you get. Now, are you expected to calculate these values? The answer to that is pretty simple. No, you're not expected to know and calculate these values. What you're expected to know is that, hey, from 19.9 you had a pH of 3.6, and at 20, exactly at 20, you go directly from 3.6 to 7. There's no other, it's a sharp increase from 3.6 to 7. It's a sharp increase. It's actually a vertical line, and then that vertical line starts to flatten out slowly and gradually, and it flattens and flattens for up until 12.52 and all of that stuff. And I am now going to show you guys the graph for it. I'm going to show you guys the sharp increase, and now you'll appreciate this titration curve and these calculations, right? So I can show it to you right here. Look at this beauty right here. So it is a strong acid reacting with a strong base, right? And when a strong acid reacts with a strong base, what initially happens? Initially, strong acid, when it was in our conical flask, right? So initially, when we measured the pH of the conical flask, it was a pH of 1, and it's right here, pH of 1. And then there's going to be a steady increase. Remember, whenever a strong acid is reacting with a strong base, there's a steady increase in pH right here, as long as the strong acid is in the conical flask, right? So there's a steady increase, and if you look at the table given to you, at 19.9 it was 3.6, right? So at 19.9, see, it's about, at 19.9 it's about in 3.6 or something, 3.5, and then there's, at 20, there's a sharp increase. The equivalence point obviously is at 7 because we know that NaCl forms and NaCl has a pH of 7 right here. Right? So when a strong acid reacts with a strong alkali, the equivalence point forms at 7. And see, it goes, oh, it's a sharp increase up until, about 10.40, 10.50, up until 10.4050. And then what happens is that after 11ish ke baad, after 11, it starts to slowly, become more and more horizontal, more and more flatter, right? So notice how the graph starts to slowly rise. It slowly starts to rise and then it starts to become horizontal, and it basically flattens off right before 13. It flattens off right before 13 right here. So at 40 cm cube you had a pH of 12.52. So see, at 40 cm cube you had a pH of 12.52. It flattened out right before 13. At 40 cm cube, flattened out right before. Obviously, if you add more and more NaOH to it, maybe the pH starts to increase. But we only are concerned with this particular volume right here. So this is how the titration curve for a strong acid reacting with a strong alkali actually looks like. Initially, there's a steady increase, and then it goes roughly from 3 till 11, roughly from pH 3 till 11, and you need to sketch this. So roughly from pH 3 to pH 11 is going to be a straight horizontal line. And where would the equivalence point lie? We know that equivalence point for strong acid and strong base lies at pH 7 right here. And then after 11, it starts to slowly flatten off. It starts to rise a little and then flattens off. So pH 3 to pH 11 is basically my vertical line, right? That's the equivalence point. And pH 1 was my starting point in this case. 1 to 3-ish, it has a steady rise to it, right? And then pH 11 has a little rise and flattens off, and you need to be able to sketch this, and that's all. Rise and flattens off. Done. Now this was when you guys actually started with a strong acid inside the conical flask. It could also be vice versa. Understand? It could also be vice versa. You could start off with a strong base in the conical flask and then you start to add acid to it. And literally it's the mirror image of the one that you saw above. It's the mirror image, because strong alkalis normally have a pH of 13. Right? So you're going to start off with pH 13. You're going to start off with pH 13, and there's going to be a steady decrease now. See, for acid, it's steady increase. But it's pretty logical. You had a strong base in the conical flask, pH 13. You start to add acid to it. What should happen to the pH? The pH should start to decrease. The pH should start to become more and more acidic. It should start to decrease slowly and gradually. It becomes less alkaline. It starts to have a steady decrease towards it. Decrease. Up until which point? Up until normally 11. And after 11 to 3, 11 to 3, that's the equivalence point. Right? That's where the vertical lines come into play, and pH 7 is the equivalence point right there. pH 7 is our equivalence point, right? The pH at equivalence point effectively. And from 11 to 3, it's that steady line. Because why is it 11 to 3? That's a question you could ask me. That is basically calculated through these values. Are these calculations a part of your course? No, they are not. So we couldn't care less. So normally it's 11 to 3. You just need to know it for now, right? Just know it for now. But inshallah, aage jaake I will even prove, and I'll give you shortcuts for it. And then after 3, it starts to steadily decrease till flattens off right before 1. Because strong acid is 1, so it flattens off right before 1. And let me show it to you right before. Just like the above one flattens off right before 13, this one flattens off right before 1. And I have to show the picture to you guys, and you need to sketch this in the exam. Right, so right here. I found out all the sketches, don't worry about it. This is the sketch. It's literally the mirror image of the one that you guys saw above. Right? इसके questions आते हैं. Sketch the graph for strong acid reacting with strong base, and the strong acid is in the conical flask. So this is what you sketch. And if the strong base is in the conical flask and you are adding strong acid to it, this is the sketch for it. You start off with pH 13. because that's the pH of the strong base. Just like here, you started off with pH 1 because the pH 1 was the pH of the strong acid, and it started to increase till pH 3.6, and the proof for it are these values. Are these value calculations part of the curve? No. Similarly here, it'll go down from pH 13 to about pH 11ish, and then there'll be a steep line right here, and then it's literally a mirror image of this, right? And you could see it right here. You could even, if you want, you could even draw it, right? It's like this, and flattens off right before 1. This is how if you started off with strong base in the conical flask, the initial pH would be this. Then this is the vertical line at 11 up until 3. After 3, it starts to flatten off, and it flattens off right before 1. That's how it looks right here. You can check it out. That's how it looks, right? And in this case, he's using 50 cm cube of NaOH. So what should be the volume of the equivalence point, the volume at equivalence point? It should be 50 cm cube. And they'll say mark the equivalence point for strong acid and strong base. The equivalence point is right here at pH 7. That's it. How easy is this? Now, the tricky part starts to come into play when you start to mingle around with this, right? So we did strong acid plus strong base. The first graph was that, and how do you sketch the first graph? We literally looked into it. For strong acid, if the strong acid is in the conical flask, what do? You start off with pH 1, move up, gentle rise till pH 3ish, then from 3 till 11, you have the vertical line, and because it's strong acid and strong base, the equivalence point is at pH 7. After 11, there's a slight rise to it. And flattens right before 13. Done? Right before 13, and you guys can see it. See? 1, rise to it, went up all the way to 11. 11 ke baad thoda sa rise, thoda sa curve, and then flattens off right before 13. That's it. Then, if you start off with a strong base and react it with a strong acid, please, not a lot of teachers are able to decipher it in such a beautiful manner that you can sketch it very easily. So if you start off with a strong base, you start off with about pH 13. So my starting point in this case is now pH 13. It will start to decrease. The moment I start to add acid from the burette, it decreases from about pH 13 all the way to about pH 10ish. It starts to decrease. 10ish 11ish. It starts to decrease, and then from 11 to 3, that's the vertical line that you see, and the pH of equivalence point is pH 7, and then from 3 onwards it starts to decrease, and flattens off right before 1. Done. So this is the accuracy with which you need to sketch these titration curves. Done. The problem arises where you start to basically mingle around with them, and you start to use weak acids and weak bases. How do these graphs look, and what would be the pH at equivalence point? What would be the pH of the salt? How can you guys safely determine this? There's a trick for this. There's a very easy trick for this, and I would expect you guys to know the trick, because mathematical calculations, I've already done 2-3 calculations with you all, but they are not a part of your course. So we came up with a trick for all of you, which are written in a couple of books. Not written in Cambridge books, by the way, but Cambridge expects students to know them. God knows why. But they are written in the Edexcel book. And I think in the IB book it's also written. I call this trick, and the books call this trick, the rule of 2. The rule of 2. What's this trick? The rule of 2 trick? It's pretty simple. The rule of 2 trick basically gives you an approximate pH of these particular reactions when you involve weak acids and weak bases. For example, I say you had a pH. What's the pH of a weak acid? Now, normally we know that pH of weak acid is 3ish, 4ish, 5ish, everywhere, yeah? So if you were to plot a titration curve, what pH should you take? It's called the rule of 2 because what you do is you take the pH of strong acid, and because you want a weaker acids have a higher pH or a lower pH compared to a strong acid. Hanji, a weaker acid has a higher pH or a lower pH compared to a stronger acid? Weaker acid has a higher pH, right? The stronger the acid, the lower the pH. So the weaker the acid, the higher the pH. And the rule of 2, it's called rule of 2 because you just add 2 to it, right here. So what should you start off with? If you have a weak acid in conical flask, what should you start off with? You should start off with pH 3 as your initial starting point. How easy is this? What would be the pH of a weak base or a weak alkali? Again, it's called a rule of 2 for a reason. What's the pH of a strong alkali? It's pH 13. Now, my question to you guys is, does a weak alkali have a higher pH or a lower pH? Come on, it's common sense. Don't rote learn them. Just know the rule of 2. Does a weak alkali or a weak base have a higher pH or a lower pH? The stronger the alkali, the higher the pH. The weaker the alkali, the lower the pH. Right? The closer it is to 7, 8, 9, all of that good stuff. So if I were to figure out the pH of a weak base, what do? Rule of 2 says what? What should I do? Add 2 to it, subtract 2 from it. Because it's a weak base, it should have a lower pH. And rule of 2 says use 2. So I'm going to use 2 by subtracting these 2, right here. And so the pH of a weak base is pH 11, right here. That's the rule. Yeah, that's the trick. Yeah. Now, if you start off with a weak alkali, it should have a pH of 11. That should be the starting point. The question is the equivalence point, which a lot of students and teachers say, but tukka hai, beech mein laga do line, or koi tukka wukka nahi, there's no, it's not tukka shukka. It's the same rule of 2 that you need to use, and this is what Cambridge recommends. All the examiner reports recommend this. I've read everything about this, right? So, it's the same rule of 2, which is what? If I were to figure out the pH of, let's suppose, a weak acid reacting with a strong base, and the pH of the salt, right? The salt of the weak acid reacting with the salt strong base, and the salt of a weak base reacting with a strong acid. What would be the pH of them? Effectively, what would be the pH at equivalence pointerino? Right? And it's very easy to decipher it. Very simple. Very simple. Dekhiye. What's the pH of when a strong acid reacts with a strong alkali? Or a strong acid reacts with a strong base? The pH is 7, right? When a strong acid reacts with a strong alkali, strong acid plus strong base or strong alkali, the pH is 7. Strong acid plus strong base, the pH is 7. That's our reference point. Now you tell me, if you now use a weak acid and a stronger base, would the pH lie more towards the basic side or more towards the acidic side? There's no rote learning to it, although this is a trick, by the way, but it's also logical. You have to use logic behind it. It would lie more towards the basic side. So what does the rule of 2 say? Should I add 2 to 7 or should I subtract 2 from 7? I should add 2 to 7. So what should be the pH at equivalence point? It should be pH 9. How easy is that? So if you are using a weak acid and a strong base, the pH at equivalence point should be pH 9. Right? What if you have a weak base but a strong acid? Should it be inclined more towards the acid side or more towards the base side? Because it's a stronger acid and a weaker base, so it should be more towards the acidic side. So the rule of 2 says, should I subtract 2 or add 2 to it? Obviously, it should be more towards the acidic side. Subtract 2 from it, you get pH 5. That is the pH of the salt at equivalence point. And this is effectively an approximate. What if we use a weak acid and a weak base? Let's talk about it. Salt of, what's the pH of salt? Of weak base and weak acid. You tell me. The strong acid and strong base pH is pH 7. Right? And if it's weak base, what does that mean? Weak base means what? It's going to lie more towards the acidic end. So I'm going to, subtract 2 from it. And weak acid means what? It's going to lie more towards the basic end. Add 2 from it. 2 cuts out. It's again pH 7. So strong acid, strong base has a pH of 7. And the salt for them. And the salt of weak acid and weak base approximately also has a pH of 7. Right? It's the same rule of 2 that we use in order to make these titration curves, because they are effectively an approximate. So let's talk about this. I'm going to first talk about weak acid reacting with a strong base. What should be the pH at equivalence point? Shabash. What should be the pH of the salt at equivalence point? You know strong acid plus strong base is pH 7. Good stuff. Okay, great. And then what am I going to do? Because it's strong base, it's going to lie more towards the basic end. So the equivalence point pH should be pH 9. Good stuff. Now, it's a weak acid that I'm starting off with in the conical flask. So what should be the pH of that weak acid? Weak acid pH, again, rule of 2. pH of strong acid is 1. Weak acid is add 2 to it, it's going to be 3. So you start off with 3 and equivalence point would be at 9, right? So you start off with 3, there's going to be a little rise towards it for it, and then it's going to be till the equivalence point is going to be at 9, and then you're going to move up and so on and so forth. So let me just show you guys the picturino for it, and you'll understand it through the picture, right? So let me show it to you. किन किन किताबों से उठाई हैं मैंने चीज़ें आप लोगों के लिए. Okay, look into this. We're adding the alkali from the burette, right? See, I've even labeled it for you, base from the burette. So the weak acid is right here. This is basically weak acid plus strong base. So weak acid, start off with what? We start off with pH 3. And you just need to appreciate the fact that when you started off with strong acids and strong bases, there was a gradual rise or decline. When you start off with a weak acid, there's a rise towards it. There's a proper rise toward it, right? When we used to start off with a stronger acid, what would happen? You guys check this out, and you need to appreciate these differences. We start off with a steady rise. We start off with a very steady rise, stable rise, steady rise. Here, if you start off with a weak acid, there's a little jump towards it. Why is there a jump towards it? Inshallah, A2 chemistry. It's because the solution is not yet buffered. What's a buffered solution? A2 acid, bases, and salts, inshallah. Take it, if I get to teach it. So, this is pH 3. Now, so you start off with pH 3 and you have to give it a little bumpy up, a bumpy ride. Why is this a little bumpy top? There's a reason for it, not a part of your course. So, a little bump, and then after that, you start off with going up right here. And from 7, normally from 7 till 11, it's a straight vertical line. So what I'm going to appreciate is pH 3 is the starting point. There's a sharp bump like this. It's like a mad A sign, It's like this sign right here, like this, right? So there's a bump to it, a hump to it, a max and a min, a max and a min. So you go like whoop, whoop, right here, and then from 7 all the way till 11. From 7 all the way till 11, it's the vertical line. But the pH of the salt you already calculated right here. See, the pH of the salt at equivalence point, pH 9. This, in fact, is the equivalence point, and the examiner normally asks you to label the equivalence point as well. So it's right here at pH 9. And understand, why is 20 cm cube of base being added? Because the volume of the acid that you guys had was 20 cm cube and 0.1 molar. So if the base concentration is 0.1 molar, what would be the volume of neutralization? 20 cm cube. So this should happen at this pH 9, this vertical line, this equivalence point should happen at 20 cm cube pH. If this was not the case, then the ideas have already been taught in the last class. You would maybe go to 40. Maybe this would be then the vertical line, or your graph would look something like this. Maybe this is how the graph would actually look if it were certain changes, right? So that's the idea. So from pH 7 to pH 11, there is my vertical line. And I've even figured out another easy way to go about it. Let's see if that way actually makes sense in my brain. Let's think about it. 3, 9, 14, and yes, it does. Yes, it does, my dears. I just came up with something else. Dears. I just came up with something else. Sir, how can we remember that this is pH 7 to 11 and the vertical line pH, this is about 3 to 11? I'll tell you how to remember. Take the average. Take the average. What average? Sir, pH, you start off with, you go from pH 3, where? To which pH? pH 11. Sir, how do I know I have to go from pH 3 to 11 in strong acid and strong base? The equivalence point is 7, right? The equivalence point is 7. So if I were to use an idea, I can say, hey, I go from 3 to 11, the midpoint of 3 and 11 is 7. Right? So you have to look into the midpoint. That's why I said take an average. 14 divided by 2, it's 7. So what I can also do is I can say, hey, what should be the vertical line, the length of the vertical line? If the pH is 7, it should be equidistant from whatever my starting point is and whatever my ending point is, right? So if it's pH 7, see, you add 4 to this, you end up with pH 7, and you add 4 to this, you end up with pH 11. So if 3 to 7, that's the increase of 4. 7 to what value should you go? Again, the same increase, increase from it. So this is my own trick. No book has it, frankly speaking. It just popped up in my brain. Similarly here, if the equivalence point is 7, the vertical line should be equidistant above and below. So you started off with pH 11 as your starting point of the vertical line. Till which point should you go? Well, 11 to 7. What's the decrease? It's the decrease of 4. So 7 to what decrease? You also have to further decrease of 4. 7 to what? 7 to 3. So the line, in fact, the vertical line goes from 11 to 3 right here. This is like a totka, a shortcut. Similarly here, think about it. Think about it. How do I know that for weak acid and strong base, what is going to be the vertical line? What would be the length of the vertical line? Pretty easy. What's the ease of it? Well, I know that the pH right here of the salt is going to be pH 9. The pH of the salt is pH 9, right? So the totka for it is, hey, I know I have to start my vertical line from 7. And so if the pH of the salt is 9, there's an increase of 2 right here. So there should be further an increase of 2. So you should go from 7 to 11. That should be the vertical bit of your titration curve. आसान है. This is called a totka. मजा आ रहा है? टोटके पढ़ा रहा हूँ आपको. क्योंकि देर आर सम थिंग्स, जैसे ओ लेवल्स में मैं टोटके पढ़ाता था कुछ एक्सटेंट तक, क्योंकि वो कैलकुलेशंस आपके कोर्स का हिस्सा नहीं थे, और ये कैलकुलेशंस अभी भी नहीं है आपके कोर्स का हिस्सा. शुरू में तो मैंने करा दिए थोड़े बहुत. नींद आ रहा है, मरमुर नहीं मजाक कर रहा हूँ, ना मरी. खैर, and similarly this is the idea, right? So if you were to talk about weak acid and strong base, weak acid starts with 3, number 1. It has a hump to it, like an increase right here, and then like this till pH 7, and then from 7 to 11, that's a vertical line. pH 9 is basically your equivalence point pH, and then from 11 there's a slight increase, and just it basically flattens off right before 13. Flattens off right before 13 right here. See, it goes up. After 11 there's a gradual increase and flattens off right before 13. But if you had weak acid plus strong base, but the strong base was in the conical flask, then you start off with pH 13. Yes sir, start off with pH 13, and from pH 11 till pH 7, that's basically the vertical line right there, and pH 9 is the equivalence point. So pH 7 to, or pH 11 to 7, and you need to know this, unfortunately. So I'm trying my level best to make it as easy as possible. So 11 to 7, that's the vertical line for you, and then from pH about, then from 7 you start to have a gradual decrease, because weak acid has a pH of about 3. So it should flatten off right before 3. See, it's flattening off right before. If this is 3, it's flattening off right before 3. So it flattens off right before 3. Done. Yes, you could say that equivalence point is the average of the vertical point, the vertical line. Or you don't have to do it like this. If you know the equivalence point, you could actually figure out the vertical line for it, even if you just know one part of the vertical line. If you know, hey, for weak acid and strong base, I have the vertical line must be from 11, right? From 7. So you could, and you know the equivalence point is 9. So just add 2 to it. So from 7 to 11, this is the vertical point, right? Because this, basically estimating this pH is pretty easy. Estimating the vertical line is the real deal, right? And you can actually do that. So that's the idea, and you need to be able to draw these in the exam. All of these graphs are testable. Teachers will just tell you to rote learn them. I am teaching you guys how to rote learn them. There's a difference, right? Okay, next. I have even given calculations, so cut me some slack. Next, sir. Strong acid and weak base, right? And we're going to start off with strong acid in the conical flask. So strong acid and weak base, what should be the pH? Sir, strong acid and strong base pH is 7, and it'll be more inclined towards the acidic end, so subtract 2 from it, it should be pH 5 right here. This should be the pH at equivalence point, right? And strong acid inside the conical flask, so pH 1, you start off with pH 1, and there's going to be a gradual increase, no humpy shumpy to it, right? So gradual increase, and from 3 up until where? From 3 it will start to become a vertical line. Up until which point? See, 5 is the equivalence point. So from 3 to 5, that's an increase of 2. So from 5 to 7. So from 5 to 7 you'll have to go, right? So from 3 to 7, from 3 all the way to 7 right here, this should be the vertical line. 5 should be in between these two. And so from 3 all the way to 7, this should be the vertical line. After 7, because it's a weak base, it should basically have a little increase to it and flatten off right before 11, right? So because weak base has a pH of 11. Weak bases have a pH of 11. So it should flatten off right before 11. So from 7, and flatten off right before 11. This, let's suppose, is 11. So flattens off. Please, these totke will help you guys loads. Okay? And I'm going to show you guys the curve for it right now. Right here. So you guys can see the base is added from the burette, which means the strong acid is in the conical flask. See, pH 1 gradual increase up until 3, 3 to 7, 5 is the equivalence point, 3 to 7 that's the vertical line, and after that it starts to increase because weak base has a pH of 11, so it will flatten off right before 11. Done and dusted. And for example, you have a strong acid and a weak base, the same idea, but now the weak base is in the conical flask. So weak base has a pH of 11. We already know why, because strong base is 13, 13 minus 2, 11. So start off with pH of 11. There's a decrease right here. Again, look at the decrease. It's not like a simple decrease like the one you studied before. Now it has a bump to it. It has a little rise to it, like this, like this. That's the decrease. You know? Look at this. It's like a mad like this decrease. Right? So there's a decrease to it, and so it starts to decrease up until from which particular point it starts to decrease. There's a little bit gradual decrease right here, and then from 7 it becomes a horizontal. It becomes a vertical line up until 3, and 5 is the equivalent point. So 7 to 3, that's the idea, and 5 is the equivalence point pH right here. And then after 3, it starts to flatten off and flattens off properly because it is going to go towards the strong acid side. So it flattens off properly just before 1. So flattens off just before, right before 1, and that's the idea, right? So you need to be able to draw all of these. Okay, relax, yeah, I'm drawing everything, relax. The last one, so we've done strong acid plus weak base, strong acid plus weak base. We've done weak acid plus strong base, weak acid plus strong base, all the scenarios. I've done all the scenarios with you. See, strong acid, strong base, something is in the conical flask, the other is in the burette. Strong acid plus strong base, one is in the, we've switched the conical flask and burette. Strong acid, weak acid and strong base right here, weak acid and strong base, but in this case the conical flask had the weak acid, in this case the conical flask has the strong base. We start off with the strong base. Similarly here, this is the idea, and that's the idea here. So I've done all the possible graphs that can come in the exam, all of them, nothing is left. The last bit which is left effectively is weak acid and weak base. Normally we don't do this. There's a reason to it. The reason why we don't do this is because in all the above cases where one of the element was strong, one of the substances was strong, either it was a strong acid or a strong base, what we understood was there was a sharp abrupt change in pH. There was a sharp and abrupt change in pH, right? And that was indicated how? That was indicated by the vertical section of the graph. Vertical section of the graph. The vertical section of the graph actually indicated that sharp abrupt change in pH, and it actually helped us properly figure out the change, change that we wanted to see, right? That vertical section was very important for all of us, and the pH was gradually changing or whatever, but the vertical section was very, very important, and you guys can see it right here. All of these vertical sections, very crucial. Vertical sections, they are actually helping us a ton. They are helping us a ton. And why are they actually helping us? Because these vertical sections will later on help you identify which indicator to use, which indicator to actually use. What should be the choice of the indicator? And the only way you can figure out the indicator is if you know that there's going to be a sharp vertical section in their titration curve. Unfortunately, if there's a weak acid and a weak base titration, there will never ever be a sharp vertical section, and therefore there's going to be no suitable indicator for it, because indicators we decide based on these vertical sections, and you'll figure out later on in this class. But there's no suitable indicator for it. No suitable indicator, because the pH, it does not have a sharp abrupt change. It does not have a sharp abrupt change. It changes just gradually, right? And so you can't have a suitable indicator for it, and it would not be possible to find the endpoint accurately. You can't even accurately find the endpoint. You can't do that. You can't figure out the endpoint. We can estimate it that it's going to be pH 7, but you can't literally figure out the endpoint, the exact endpoint. It's not really possible, you know. And no indicator is suitable for such type of neutralization reaction. And so how do we measure the pH? We literally estimate it either, or we measure it using a pH probe or a pH meter. So you, instead of using an indicator, you use a pH probe or pH meter to identify the endpoint and the pH when the endpoint has been reached. And this is the graph for it. So we normally don't draw these graphs, and we don't even use them. It's useless. Weak acid and weak base has no vertical section to it, because it's such a quick reaction. It's such a quick reaction that there's no vertical section of it, because weak acid, weak base, tak to khatam. That's it. Tak to khatam. Right? So look at this. Look at this. There's no vertical section towards it. Start off with 3. The weak acid was in the conical flask, and it start off with pH 3. There's no vertical section to it, just at pH 7, and just, you know, rotate it a little, and that's it. So this is the weak base and the weak acid titration, and you'll never be asked to sketch it. This particular sketching is not part of your course because it's useless, but somebody has made a stimulation for it, so I wanted to share it with you guys. It's useless. Weak plus weak is useless for us. So this stimulation has been made, but normally in labs and anywhere and everywhere, we don't do weak acid plus weak base, because there's no point in doing it. You don't even have an indicator for it, right? And you'll know why I'm saying you don't have an indicator for it and you won't get endpoint accurately, because the vertical section will actually help you guys choose the indicators, right? Now, the summary for this particular class, and we're done with titration curves, right? So the summary for this particular class is, I wrote it before the class. I had a picture. I wrote it somewhere. I think I had a picture. I snippeted out a picture, and this will help you out a lot. This is the summary of the entire class. You guys can give it a look. See, if it's a strong acid, strong base, the initial, this is in the flask. So if the acid in the flask, the initial pH is 1. This is effectively the entire summary of whatever I've taught right now. So strong acid, pH of 1, strong base, pH of, strong base, normally pH of 13, right? Now, when they do react, the equivalence point is pH 7, and I even taught you how to calculate. You can either rote learn this entire table, but I've taught you guys how to calculate stuff. And see, it's from 3 to 11. It's going to be the mid 3 to 11. You know the starting, the point in which the vertical section starts to begin is 3. So it's 4 below 7, and so just add 4 more to 7. That's 11. That's how I always remembered it throughout my life. I also know calculations for it, but again, calculation is not a part of the course. You just have to know it. And flattens off just before 13. This flattens off just before 1. This weak acid, strong base flatten off just before 13, but you start off with 3. And this is 9. See, whatever I've taught you guys, however I've taught it to you guys, if you are good rote learners, you can just start rote learning this. But if you want to use logic and remember it through these totkas, you can absolutely do so. Right? Easy peasy lemon squeezy. This was all about titration curves. All the prerequisites that I was giving you guys was for this particular day. Yes. Now, last concept, and we're done with this chapter. Choice of the indicator. This is the most tested question in MCQs and even in the exam. Which indicator to select? Now, remember, it's very simple. Very simple. And I give you the trick to figuring out which indicator you must select for any type of reaction. And the trick to that is, in order for an indicator to work, remember this, in order for an indicator to work, the range of the indicator must lie. The range of the indicator must lie completely within the vertical section. it must lie completely within, the range of the indicator must lie completely within the vertical section of the titration curve, and that's it. That's it. That's how you can figure out which indicator to use. Normally what you realize is that if it's a strong acid and a strong base reacting together, the pH is, the vertical section is from 3 to 11. And the two indicators that fall in this particular range are normally methyl orange. That's why in O levels and IGCSE you were normally given these two, methyl orange and phenolphthalein. Done. And whenever it's like a weak acid and a strong base, or vice versa, the range is 7 to 11. And normally here only, I think if I'm not wrong, it's only thiamoil blue which is going to work, and phenolphthalein will also work. They will give you the right results here. Phthalene. They will give you the right results, right? Now, do you need to know this by heart? No, you don't. You don't need to know this by heart. You should know the idea of using them. I'll show you the table. I'll show you a table right now, and I'll show you a couple of graphs, and we're done with the course, with this chapter. The table is right here. This is the table of indicators, and this is their pulse. That's why now you know why you needed to know all of these indicators, because these vertical sections are what dictates which indicator do you actually use. And you see, methyl orange has a range of 3.1 to 4.4. Now I'll show you something. 3.1 to 4.4, and you love this, inshallah. You'll love this. Right here, let me show it to you. It's all visualization. A levels is all about visualization. Right here, let me put the last picture as well. Where's the last picture? Right here. Right here. Now see. Methyl orange has a range of what? 3 to 4.4, right? It's about 3 to 4. And look at this. It's 3 to 4. Does it lie on this vertical line? 3.1 to 4. Is it lying on this vertical line right here? Is it? Yes, no. It's just a yes, no question. It's just an yes, no question. Is it lying on the vertical line, sir? Is this lying on the vertical line? Absolutely it is. And if it's lying on the vertical line, what does that mean? Can I use methyl orange as my indicator? Absolutely I can. It's weak acid and weak alkali and strong acid. And in this case, strong acid is the one that we're starting off with effectively. I can use methyl orange. The question is, can I use phenolphthalein? That's the question. Can I use phenolphthalein right here for weak alkali and strong acid? Can I use phenolphthalein? Remember, look at my wordings. Please look at my wordings. The range of the indicator must lie completely within the vertical section of the titration curve. Is phenolphthalein lying completely within the vertical section? Just a slight touch to it. It's all the way above. So I can't use phenolphthalein. And that's why methyl orange is the indicator that I'm going to use if I were to have a strong acid and a weak alkali, right? Let's look into strong acid and strong alkali. You can use both phenolphthalein and methyl orange, tick and tick, because both ranges lie on the vertical section, right? So this will actually show you a color change. How easy? How easy is this? Next, if I use a strong alkali and a weak acid, can I use phenolphthalein? Absolutely I can. What's the range? The examiner will give you the range. Look, phenolphthalein is 8.3 to 10. And you'll see here, 8.3 to 10. It literally falls on the vertical line right here. So you can absolutely, lies completely within the range of the vertical line, of the vertical section of the titration curve. So you can use phenolphthalein. Methyl orange, can I use? No, I cannot. Right? In strong acid and strong alkali, you can use both. In strong acid, you can use methyl orange but not phenolphthalein. And in strong alkali and weak acid, you can use phenolphthalein but not methyl orange. And that's why we do not perform this particular titration, because you can't literally have an indicator for this, because look at the phenolphthalein. Phenolphthalein is actually lying, there's no vertical section to it, so you can't use any indicator for it. Phenolphthalein is even lying above, and this is methyl, and there's even no vertical section, so there's no indicator for this. That's why in practical life we don't even do this stuff, and that's it. And see, that's the idea that's been given to you. So in the exam, in MCQs, you'll see you'll be given the ranges of, there's an indicator X, it has a range of this, where can it be used? And you should know the vertical lines, the range of these vertical lines, in order to figure out whether it would fit or not, right? And so one last picture I want to share with you guys and we're done, is this picture, and we're done. Chapter over, guys. Enjoy. Tomorrow, inshallah, we're going to start off with reaction kinetics. बस यही था इसमें. Look, strong acid, strong alkali. Yes, you can use both methyl orange and phenolphthalein. Methyl orange and phenolphthalein. Strong alkali but weak acid. You can use phenolphthalein but not methyl orange. Strong alkali but weak acid. And weak alkali but strong acid. You can use methyl orange but not phenolphthalein, because it does not lie on completely. The range of phenolphthalein does not lie completely within the vertical section. And if it's weak alkali and weak acid, none. No indicator. So I hope that titration curves are now easy, and from these totkas you are able to actually sketch them later on in life. Done? Any questions, guys? Khatam. Acid, bases and salts is done.